Okay, so there was one point from the last video that we didn't have enough time to go over, which was why are these assignments that we've made versus of theoretically what the energy should be different from what the experimental IR spectrum says they are. For example, we've assigned 3020 T2 fundamental. We know that that energy is 3020 from the Raman spectrum. Why is it different from in the IR spectrum? Okay, and this has to do with something called Fermi resonance, which causes mixing of modes with the same symmetry and similar energy. This can cause, this actually causes an increase in the intensity of combinations or overtones, which are intrinsically otherwise weak. The way to think about this is it's exactly what happens when you mix orbitals of similar symmetry, and that causes the energies to separate. So as we'll see later, and you've probably gone over this before in previous classes, to make a hydrogen bond, to make an H2 molecule, right? You have two atomic orbitals. Those have the same symmetry. They both have s orbital symmetry, right? They're like one s orbital. They're both spheres, essentially. And you bring those close enough together where you can form a bond, and then you're going to get a bonding orbital and an anti-bonding orbital. And we'll go all into detail on this in chapter 5. But you had two things of similar energy, in that case the same energy, and you formed a bond, and then you got two states that were driven apart in energy to form those bonding and anti-bonding orbitals. So that's exactly what is happening here. And so here's that shown pictorially. You have two s orbitals that are this time similar in energy but not the same energy. You can see the higher energy one gets driven up further higher in energy to make like an anti-bonding interaction. The one that started out lower in energy is going to be driven even further lower in energy, right? And the degree of overlap is dictated by how similar they are in energy, and that they have to be, of course, in the same symmetry. As we'll see later on, the overlap integral will be equal to 0 if they're not the same energy, for reasons that the same exact reasons we talked about here, where you have to have an A1 or an A1G in your intensity integral in order to have a non-zero value, okay? So that same idea, this idea of Fermi mixing, is happening here. Here was the 3020 value of the T2 stretch that we got from Raman spectroscopy. Raman spectroscopy was simple. It gave us the exact energetics of those normal modes, but in IR it's more complicated because you have this mixing. And so that mixed with this 2832 combination mode, that drove up the 3020 to 3040 where we see it in the infrared spectrum, and it drove down the 2832 down to 2823 from the theoretical value of 2832. Same thing with this 1714 mode. This was our, let's see, we'll go back here. So 1714 was one of our combinations that we calculated, T2 minus T2. And our fundamental we calculated was 1306. We observed a peak at 1300. So this 1306 peak got driven down by mixing with the combination at 1714. And the 1714 got driven up to 1720, which is where we observed it. So what is happening physically when you get a mix? Well, you actually get, a mixture of states. There's some character, just like when you bring two atomic orbitals together and you get mixing, or two molecular orbitals together and you get mixing, you have character that's based on the constituents. You have character here that's based on the constituents as well. So let's just go over the Raman spectra. We had 3020 T2 asymmetric stretch, 2019-14, that was our A1 symmetric band, 1526 was our E symmetric band, 1306 was our T2 asymmetric band. These, again, we were able to hone in on which one was which once we looked at the infrared spectrum. From the Raman spectrum alone, all we knew was these two for sure. The polarization helped us with A1, but we didn't know whether or not the E, right, was 1526 or 1306, and same thing with the T2. We knew they're one or the other. Once we looked at the infrared spectrum and did kind of this puzzling out, we're able to figure this, assign these with certainty. But this is where things are interesting. Now you have this mixing. And so you can see this 1320, right? That is where this 1340 came from. So it's primarily a T2 asymmetric stretch, but it's Fermi coupled to a T2 bend plus an E combination, okay? Because that's what it mixed with. And the 2823 that it mixed with was the T2 bend plus the E combination, but it's Fermi coupled to the T2 stretch normal mode. So what does this look like pictorially? I mean, it's kind of difficult to actually show you, but it would be, you know, some fractional contributions of all these different modes. So mostly, you know, this mode is going to look like that T2 asymmetric stretch, where one of the bonds is moving 3 times faster than the other 3 are contracting in the opposite direction. But there's going to be a little bit of bending going on with a T2 bend and an E bend. So it's going to be a kind of complicated mixture of modes here. And similarly, the 1720 and the 1300 behave similarly, right? The 1720 was primarily this combination mode of a T2 stretch and the T2 bend, but then there's going to be a little bit of the pure T2 normal mode in there, and exactly the opposite for 1300. And so the last point I just want to make is this is the reason why these particular bending mode, these particular combination modes appear in the IR spectrum. As we saw from the selection rules, there are many different overtones and combinations that were allowed by group theory, right? Group theory told us we could actually have 8 different commutations. Now, some of those, 8 different combinations. Now, some of those were outside of the range of a normal IR spectrum, or they had negative energies. But we didn't see, you know, 12 different peaks or 10 different peaks or even 8 different peaks. We only saw 4 different peaks in the experimental spectrum. And that's because in most cases, in order to see these weaker combination modes or overtone modes, you need there to be some Fermi coupling to enhance the mode. Because once you are coupled to a normal mode, which has very high intensity, the overall intensity can increase for these less intense modes such as overtones and combinations. So the fact that the energetics work and that these combinations had similar energy to fundamentals allows them to appear. So that's kind of cool. And then just the last thing I would say, just in terms of course mechanics, is that, you know, this is a very simple molecule, right? Methane. You could imagine doing this sort of infrared and Raman spectroscopy analysis for more complicated molecules, and I encourage you to do that in your research should those situations arise. And I think this could be, you know, very useful for you, having this framework about instead of just, you know, looking at a table of organic molecule functionalities, you can maybe start thinking about it from a group theory framework. Could give you some additional insight. But it's already extremely complicated, even for a simple molecule as methane. And so what I just want to say is that, you know, I'm not going to test you on this sort of analysis. I want you to appreciate this. But what we've gone over in the last video in particular, right, the interpreting IR spectrum video, that sort of table analysis and puzzling things out, I'm just going to tell you upfront, I'm not going to give you that on the exam. And the reason is not because I don't think it's a good problem. It's just because it would take too much time for you to figure out, and I want to, you know, make sure I'm testing you on a wide variety of topics on the exam. So any of this stuff, of course, is fair game for the homework, but for the exam, you don't have to worry about, you know, practicing these skills. It's mostly just simple logic. The logic can be complicated and hard to keep track of, but if you're organized, it's mostly simple logic and it should be quite manageable. So I don't feel like I have to test you on this sort of skill.